In this video, I'm going to talk about the classification of the stars. So first we begin by imagining a scenario. So this is our sun, right? Our sun has a core. This is where fusion happens, right? Because this is the densest part or the highest temperature part of the sun. So that's where the fusion happens. And there's something called a stellar plasma, which is, let me use a different color here, which is what make up this part other than the core. So all these are stellar plasma, right? So what happens is when fusion happens in the core, like the light, they has to diffuse through this sort of stellar plasma. And in this process, they could be absorbed by what made up these stellar plasma. In a lot of cases, hydrogen, right? They could be absorbed by these hydrogen. So we have a formula here that tells us that in order for energy, the absorption wavelength is as the follow. So the absorption wavelength from one level, level n to level m, is equal to hc over em minus e. And so what does this mean? Like you could figure out, okay, what is the absorption for, let's say, hydrogen? I want hydrogen's energy level to go from 1 to 2, right? Then that can happen because in one of my early videos, that can happen through an absorption of a photon. So, but that photon needs to be at a specific wavelength, and that wavelength can be calculated in this case. Could be hc over e2 minus e1, right? And then there was also a formula where you talk about en for hydrogen, right? So what this formula tells us is that when it jumps from one level to another level, let's say for hydrogen, it can absorb a photon to achieve that, but that photon needs to be in a specific wavelength, and that wavelength can be calculated through this formula, or this formula right here. So after talking about that, then we can look at this chart, right? Like for example, we're looking at hydrogen here. So we have the Lyman series and the Balmer series. In the Lyman series, the transition all starts from 1, and in the Balmer series, they all starts from 2. So what that means is that the Lyman series are talking about hydrogen when they transition from 1 to higher level, whereas the Balmer series is referring to when it's from 2 to higher level. So that makes a difference in their wavelength, as you can see here, right? They all have different wavelengths here. In the case of the hydrogen Balmer series, they're in the visible spectrum, at least close to the visible spectrum, and then in Lyman series, they're more shifted towards infrared. And so this is what we call, like, for example, something very common is the hydrogen alpha, right? So what this means is that let's say I have a hydrogen atom. So this is the core of a proton, and then let's say it's got 2 level, right? So this is level, let's say n equal to 1. This is n equal to 2. So hydrogen, and let's draw another one. It's really bad circle I'm drawing here, but you get the idea. N equals to 3 at the outer layer. So what this is referring to, hydrogen alpha in this case, would be the specific wavelength of light needed to jump from level 2 to 3. So when it goes from 2 to 3, right, this going to a higher level can be achieved by absorption of a photon. In this case, the photon or the wavelength, it needs to be the wavelength of light that can make a hydrogen atom to go from n equal to 2 to n equal to 3 is at 656.3 nanometer in that case. Right, so this is what the chart tells us, is that is how we name these things, where hydrogen could jump from 1 to many levels or 2 to many levels. It's basically talking about the same thing, but at a different starting energy level. And now we can look at this chart. Oh, this is interesting. So what do we have here? Well, the x-axis here is the wavelength, and the y-axis is the flux. So this tells us we have the wavelength versus the flux. So as you can see, the wavelength gets shorter as it goes from right to the left, right? And in this process, you can see like hydrogen alpha absorption lines right here. Like this is about like this, like if you look at this as well, 656, right? It matches with what we have here. So what happened is that light at this specific wavelength get absorbed by the hydrogen atoms, and then you have hydrogen beta here, right? This is like 4,800, so 486 is like 486. So you get the idea here. That so this tells us that you can see that there's a dip here. There's a dip, another dip here, and there's a dip here. What these dips tells us that there's a decrease in flux at these wavelengths, and that is caused by the absorption of photon, because at these wavelengths, hydrogen actually absorbs the photon to jump to a higher level. That's why there's a decrease in flux, right? Because the flux reflects the intensity of the light, and there's less light at these wavelengths because they're getting absorbed by the hydrogen atoms. And then if you look at the left, what's even more interesting here is that something called the Balmer's jump happens. So the Balmer jump happens here. It's like the reason why there's a jump here, like the flux instantly goes down here, because what does that imply? That implies there's a lot of absorption compared to before. Well, that is actually because photons, when they increase, like photons get fully ionized, right? Oh, no, not photon get fully ionized. Hydrogen get fully ionized by the photon, and that's gonna cause, because remember, right? If hydrogen can bring electrons in the hydrogen to a high level, they can also ionize. The hydrogen if the energy is high enough. In this case, what this jump tells us is that there's a huge decrease in flux, because when the wavelength is shorter, remember, when the wavelength is shorter, the light carries a higher energy. And in this case, when the light carries a higher energy, it is actually high enough to ionize the hydrogen. And then this ionization of the hydrogen makes the hydrogen absorb that photon, right? So in that case, the flux decrease in this case, because the hydrogen absorbed, because the light is high enough for them to ionize. And then in that ionization, the hydrogen atom absorb that photon. So that's why there's a decrease in the flux state. So now we actually look at the classes, how we define stars. Like you could maybe, like, when you're on Wikipedia or any other platform, you see that there's they talk about O-type star, A-type star, or F-type, G-type. Like, what does these type even mean? Well, here we have it. Well, one distinction you can see is that, well, the lowest classification we have is M, and O at the top. So you can see that M has a very low temperature versus O. So that's one of the distinction between the classes, right? Like, we classify them by their surface temperature. Like in O-type star, the surface temperature is much higher than an M-type star. And then these have some characteristic in terms of their spectrum. Like, okay, when you're very low temperature, some molecular bands exist, right? There's bonding between the molecules. Because remember, what happens when temperature gets high is that these molecules shakes, right? The bond becomes unstable and they break when the temperature is high enough. So in a very low temperature star, in this case, an M-type star, the temperature is actually low enough for these bands to exist, right? It's for them to not break. So there's some strong molecular bands here. And there's also strong neutral metal. What that means is that there are metals that haven't been ionized. They're just metal sitting there. There's barely any hydrogen yet. And hydrogen here is very faint. That is because the temperature is not high enough to raise the hydrogen level, right? And then as the temperature gets higher, you can see, okay, once you get to K, then this becomes strongly neutralized and singly ionized metal. What this means is that when the temperature is higher, there's more energy, and that higher temperature can ionize now singly ionized. So take one electron away from these metals, right? And then hydrogen is still faint here because the temperature again is still not high enough for hydrogen to ionize. And then as it gets higher and higher, climbs up, let's say we talk about A-type star, you can see hydrogen lines at their maximum. So what this means is that at this temperature, hydrogen is getting fully ionized. So that's why their lines are at their maximum. So you can see here, like the distinction is that at lower temperature there are bonds, there's neutral metals, and then as the temperature goes up, there are more singly ionized metal, and then as the temperature goes even more up, the hydrogen gets enough energy to become ionized that that hydrogen lines start increasing, right? And then hydrogen lines eventually is gonna increase to at one point, like if you look at B, right? If you look at B, it went from maximum to moderate, because at that point the temperature is so high that it has fully ionized the some of the hydrogen. So in that case, there wouldn't be any jump between levels, right? Because when we talk about H lines, we're talking about these jump transition, and then all these energy are less than 13.6 eV, because this is the jump, let's call it, right? Because this is the energy it takes to ionize the hydrogen. So what happens when the temperature gets too high is that the temperature is so high that it fully ionizes the hydrogen. So now there's no longer jumps, right? There's no jumps of electrons or something like that if the electron is gone by the ionization. So that's what happens. That's why when the temperature is high enough, it becomes moderate, because it fully ionizes the hydrogen. And unlike A-type star, where the temperature is just high enough to excite the electron to different energy levels, but not high enough to ionize it, right? And then as you get higher and higher, right, it's helium. Then it's helium strong, because helium takes a lot of energy to make their electron and jump energy levels similar. Same logic as how hydrogen reaches its maximum. And then hydrogen becomes faint here, because this temperature, when it's beyond 30,000 Kelvin, it's so high that it ionizes most of the hydrogen, and there's no hydrogen lines emission when there's only one proton left, right? There's the hydrogen has been ionized. And then multiple ionized metal strong here, right? Because, well, when you reach higher temperature, then for example, like the temperature at G-type star might be enough to rip one electron from to take away one electron from the metal. And then when it reaches beyond beyond 30,000 Kelvin, and it's actually enough to take away even more, right? That's why we call it multiple ionized metal. So this is the classification of stars, right? And there's a way to memorize these, which is called OB. So OB, a fine girl, kiss me, or guy, depends on your preference, right? So OB, a fine girl, kiss me. So that's how you will usually memorize these classification. And remember, they have a very distinct temperature difference, and they have their own spectral characteristic. And I didn't talk about the color here because, well, remember what I talked about in the Planck. I think I talked about this in the not in the Planck, in the Boltzmann distribution video, that as the temperature gets higher, the intensity at which the maximum wavelength is emitted shifts towards the left, right? That's why it becomes blue, right? So I think I talked about this because lambda max is dependent on the temperature, and as temperature gets higher, lambda max becomes shorter, or shift towards the left, if you like to call it, and then it goes from red to blue. That is the reason why. If you're watching this video and you're wondering why that is, you might want to take a look at my Boltzmann equation video that I did. So this is a basic introduction to the spectral classes of the stars.